A common and important task of chemical engineers is to control systems, to keep a process at a specified operating point, even if other forces are trying to pull it somewhere else. To make a system robust. Once the chemists have figured out the chemistry, figured out the ideal operating parameters, it is the engineer's job to carve a path for that to happen on a large scale. Good design contributes most significantly to the efficacy of a process, one that requires the least amount of corrective action to stay on target. Once a process has been designed intelligently, the next biggest factor contributing to its performance is the control system. The control system is what will make automatic corrective actions to keep whatever process it's controlling where it's supposed to be. There are many different types of control systems, many of which begin with a model of the system they are controlling. There are many ways to create a model of a system, each with its benefits and drawbacks. This video series aims to introduce some of the most common modeling methods and to show how models can be created and used to control a chemical system, as well as to give the viewer a sense for when one approach should be used over another. Chemical processes can be understood through many lenses. Fundamental, or first principles modeling, is based on the ability to mathematically represent the fundamental processes which make up a system. Models created from first principles offer insight into the root-level nature of a system, allowing for easier troubleshooting, enhanced intuition, and careful extrapolation. Many different systems can be accurately modeled with relatively few fundamental modeling principles. The accuracy of a first principles model is based on the engineer's awareness of the components in a system and their ability to represent each component mathematically. As no model is perfect, it is important to consider the model only within the boundaries and goals it is created for. In this video, the procedure for the creation and subsequent analysis of first principles models is presented. First, let's take a look at the big picture. Any modeling process can be broken up into 6 basic steps. First is to define the goals. What variables will your control system need to control? Which variables will you need numerical values for, and which ones can be implicitly defined? How does one variable affect another? How accurate does the model of your system need to be? 2 is to prepare information. Draw a picture of your system. Find out which variables you can control, and of those, which ones you need to control. What assumptions can you make about your system? 3 is to formulate a model. Write your balances, and make sure that if something goes in, you know what will happen to it, what things it will change, and where it winds up. Leave nothing unspecified. Step 4 is to determine the solution to your model. Step 5 is to analyze results. Before we validate the answers, do they make sense? Are they within the range of the model? What approximations or assumptions had to be made to get that answer? Is the solution stable? Is the solution sensitive or robust? Step 6 is to validate the model. Do your predictions match reality? Is it accurate over the whole range? Do the model's theoretical limitations match reality? So let's start by defining the goals. With any physical system, the control goals are most easily recognized by first gaining an understanding of the system's mode of operation. Any system may be represented in basic terms as one or more inputs, a process, and an output. For many problems encountered in academia, the goals are given in the problem statement. However, when designing a new system or when analyzing an existing system, the engineer must understand the process well enough to know which variables can and should be controlled to achieve a goal. As is true of many engineering problems, a good first step is to draw a picture and identify key variables and boundaries. So consider the system illustrated here. We have a flow of liquid, F sub 0, with a concentration of chemical component C sub A0 dissolved in a solvent, flowing into this tank, where it is perfectly mixed. The tank has a constant volume, V, and when the flow stream coming into the tank flows in and is mixed with the contents of the tank, it forms this new concentration, C sub A. The liquid then flows out through this weir, through stream F sub 1. The concentration of chemical A in stream F sub 1 is the same as the concentration in the tank because we're making this assumption of ideal mixing. Looking at this system, it is intuitive that if the concentration of component A in the inlet stream hasn't changed in a long time, then the concentration of A in the tank, and hence in the outlet stream, will be very close to the concentration of A in the inlet stream. It may thus be desired to know how the concentration of A in the outlet stream will change if the concentration in the inlet stream changes. In this process, assume the outlet flow feeds another process downstream, which cannot operate until the concentration of A has reached 90% of its steady-state value after a step change in the input concentration. It will thus be necessary for the model that we create for this system to indicate how long it will take for the concentration of A in the tank to reach 90% of its new steady-state value after the step input change. Before a mathematical model of a system can be created, the boundaries of the system must be defined. The boundary must encapsulate a region, known as a control volume, in which the properties of interest do not change with position. Systems with no spatial variation of the variables of interest are known as lumped parameter systems. Conversely, systems in which the variables of interest vary with position are known as distributed parameter systems and must be modeled with partial differential equations. In this example, the tank is considered to be well mixed, so the concentration of A may be considered constant throughout the tank and in the outlet stream. The control volume for this system can be represented by drawing a dashed box around the well-mixed region of the tank. In addition to bounding the system and identifying variables of interest, any assumptions upon which the model will be formulated must be stated. Assumptions about a system can simplify the modeling process, but also limit the accuracy of the model and the domain for which the model is valid. It is important to make only valid assumptions and to make as few as is necessary to aid in the modeling process. Good intuition regarding assumptions comes from a good understanding of the system to be modeled. For this example, 3 conditions are assumed to be true. 1. The tank is well mixed. 2. The density of solvent and chemical component A are equal, and this assumption assists in the validity of assumption 1 that the tank is well mixed. And 3. The system is initially at steady state. So before we begin observing the system, the concentration of chemical A in the tank is equal to the concentration of A in the inlet stream. Additionally, we're given some data about this system. The flow rate of the inlet stream is 0.085 meters cubed per minute. The volume of the tank is 2.1 meters cubed. The concentration of A in the tank initially is 0.925 moles per meter cubed, and the change in concentration in the inlet stream will be also 0.925 moles per meter cubed. So the concentration of chemical A in the tank after the input change is going to be the sum of these two values, which is 1.85 moles per meter cubed. First principles models are created from 2 fundamental types of relationship: conservation and constitutive. Conservation-based modeling, in the context of chemical engineering, is an application of the law of conservation of mass, momentum, or energy. The general form of a conservation model is accumulation equals in minus out plus generation minus consumption. Note that some textbooks will omit the consumption term, treating it as negative generation. In this example, material is the object of study, so a material balance can be performed either for the entire flow in and out of a system, in which case it is called an overall material balance, or just for one component of the flow through a system, in which case it is called a component material balance. For the system described in this example, the concentration of A is the variable of interest. Modeling begins by performing a component material or mass balance about the system boundary. Because component A is not reacting, the generation term can be eliminated from the general form of the law of conservation of mass to yield accumulation equals in minus out. The component mass balance for the system described in this example is formulated like this. The concentration of A in the tank is in units of moles per meter cubed. Multiplying that by the volume in the tank gets us just to moles. Because this is a conservation of mass application, we have to multiply it by the molecular weight to get to a unit of mass, in this case, grams. We're interested in how this value changes with time, so we're taking the time derivative of this grouping. This is equal to the flow into the system, which is again in meters cubed per minute, times the concentration in that inlet stream, which is in moles per meter cubed. Multiplying these terms gets us to moles per minute, and then multiplying by the molecular weight gets us to grams per minute of component A. The same can be said about the outlet stream, where F1 is multiplied by Ca, which is the concentration in the tank, and then again times the molecular weight of component A. Notice how the differential mass balance resembles the form of the general mass balance equation, where this term represents the accumulation, this is the inlet flow, and this is the outlet flow. If the accumulation term were equal to 0, that is to say if the tank had 0 volume or the inlet concentration was always constant, this equation would be algebraic, simply equating in and out. In this example, the liquid flows out of the tank through this weir system. If the tank were not already full when we began observing it, then there would be some time that was required for the tank to fill up and for the liquid to reach the level of the weir. If we were to want to model that, we would say that the flow out of the tank is equal to this weir equation, where some scalar constant k sub f is multiplied by the square root of the level in the tank minus the level of the weir. And that's just referring to the difference between the level of liquid in the tank here and the level where the weir begins. Now, in this example, we're assuming that the tank was already full to the level of the weir at the moment that we began observing it. That is to say that the change in volume with time is equal to 0. This affords us the equality that the flow into the tank is equal to the flow out of the tank, and that the volume is constant. With these equalities, we can rewrite our differential mass balance from above as this down here. Notice that the molecular weight and volume have been factored out of the differential because they do not change with time. And notice that the subscripts from f sub 0 and f sub 1 have been removed and substituted just as flow f. So this is our solution equation. This is a linear first-order ordinary differential equation that is not separable. So what does that mean? A differential equation, by definition, is an equation that relates some function with its derivatives. That function is unknown, so the meaning of solving a differential equation is finding what that function or set of functions is. The function is the solution to the differential equation. If the highest exponent found on a variable in that function is 1, the function is said to be first order, or linear. By comparison, a highest exponent of 2 is second order, or quadratic, and a highest exponent of 3 is third order, or cubic, and so on. Note that the term first order used to describe the solution function has nothing to do with the order of the differential equation. The order of a differential equation is defined by how many times the solution function has been differentiated in the differential equation. So in this differential equation, we are only taking the first derivative of the concentration, and so this differential equation is first order. Ordinary refers to the number of independent variables the solution function has being 1. Because the tank is assumed to be perfectly mixed, concentration varies only with time and not with space. Additionally, solution functions that vary only with time in the context of differential equations are known as forcing functions. The differential equation is not separable, which means that the equation cannot be algebraically manipulated to position all terms containing the output variable c sub a multiplied by its derivative dca on one side of the equal sign, and to have the input variable t multiplied by its derivative dt on the opposite side of the equal sign. Separable differential equations are easy to solve by simply integrating both sides of the equation with respect to each's variable. It follows that the equation could be easily solved if it could be made separable. This can be accomplished by the introduction of an integrating factor. But first, the differential equation is rearranged into the so-called standard form. This removes any coefficients from the differential term. Before proceeding to the integrating factor step, notice a property of this differential equation. Volumetric flow rate and volume are both constants with related units. Volume divided by flow rate gives a constant time, which is an important characteristic of the system. For instance, imagine how the concentration of component A in the tank would change in response to a step input change at different flow rates. A faster flow means that the tank would approach its new steady state value faster. Also realize the effect of the tank's volume on the time it takes to reach the new steady state. A very small volume reaches the new steady state very quickly. Combining these two variables into one lumped term gives the engineer insight into the agility of the system. The lumped term, termed the characteristic time, is represented by Greek letter tau and is equal to the volume divided by the flow rate. For the values given in this problem, the volume divided by the flow rate is equal to 24.7 minutes. The differential equation can be rewritten to include this time constant tau, as is written right here. Now that the differential equation is in standard form and we've included the time constant, we can apply the integrating factor, abbreviated IF, which is equal to e to the integral of 1 over tau, which is this coefficient, with respect to time. If we work through this integral, we find that it is equal to e to the t over tau. So we take this integrating factor and we multiply it to both sides of our differential equation, and that looks like this. Now there's something special we can do with this term of the differential equation, where we say that e to the t over tau times 1 over tau Ca is equal to c sub a times the derivative of our integrating factor with respect to time. This identity is going to allow us to combine like terms with this first portion of the differential equation. So we rewrite it as this, including the identity that we just created, and then that allows us to combine these terms into one single lumped term. Now, you may notice that this form of the equation is separable. We can just multiply over this dt to this other side, and we'll be all set up to integrate both sides and generate our solution equation. So I've moved the dt over to the right-hand side of the differential equation and integrated both sides to yield e to the t over tau times the concentration in the tank is equal to the concentration of the inlet stream times e to the t over tau plus I, which is a constant of integration. Now we can solve for c sub a by dividing through by the integrating factor to get this equation here. Notice that the sign of the exponent on our integrating factor changes when we do this. If we wanted to solve for this constant of integration I, we can say that the concentration in the tank is equal to concentration of A initial at time equals 0. This was stated in the problem statement. So setting C sub A equal to the concentration of A initially equals C sub A plus the constant of integration times e to the negative 0 over tau, because it's at time equals 0, we can solve and say that I is equal to C sub A init minus C sub A 0. Applying this identity into the equation from before, we can say that the concentration in the tank is equal to the inlet concentration plus this equality for I that we just came up with times the inverse integrating factor. And this equation represents the concentration of A in the tank as a function of time, and all of the variables can be plugged in for, so this is our solution. To test whether this model satisfies the boundary conditions of the problem, we evaluate it at time equals 0. So following through, plugging in the values given in the problem statement, we find that the concentration at time equals 0 is equal to 0.925 moles per meter cubed, which is the initial concentration. We also evaluate the equation taking the limit as time approaches infinity, and we find that the concentration after infinite time is 1.85 moles per meter cubed. This corresponds with the new steady state value after the step change in the input concentration. So these values indicate that the solution exhibits the appropriate boundary behavior that we would expect for this problem. For this example, testing the boundary conditions is sufficient to proceed to further analysis and quantification. For other problems, additional tests may be applied depending on the predicted form and complexity of the solution. Plotted on the screen now is the change in concentration C sub A in response to the step input change. The step input change is applied at 20 minutes to show how the system is at steady state before the step input change. The slope of the response curve is steepest in the instant after the step change input, and slowly tapers off as it approaches its new steady state value. For the calculations I'm about to show, the step input will be considered to have occurred at time equals 0. So the graph of the response curve would look like this. Now the problem statement asks how long it will take for the concentration to reach 90% of its new steady state value. The 90% value of the change in concentration is calculated as follows. We just take 0.9 times the change in concentration equals 0.8325 moles per meter cubed. Adding this to the initial concentration, C sub A init equals 0.925, we get that the 90% concentration will be 1.7575 moles per meter cubed. Solving our solution equation for time, we find that T is equal to negative tau times the natural log of the concentration of A in the tank minus the inlet concentration divided by the initial concentration minus the inlet concentration. To solve for how long it will take to reach this 90% concentration value, we simply plug in the 90% concentration into this equation, and we find that the time will be 56.87 minutes. Plotting that on the graph, we can see that the concentration does appear to be at about 90% of that output range, so it does seem like this model is valid. Another interesting property is if we evaluate the concentration at time equals tau, we find that it equals 1.51 moles per meter cubed. Evaluating what the percentage of the total range that 1.51 moles per meter cubed represents, we calculate that it equals 63.2% of the output range. Plotted on the graph, this is where that falls. The value of 63.2% is not unique to this problem. The value of any curve responding to a step input change will be 63.2% of its range when evaluated at the time constant for the system, so long as the response is not delayed. In this problem, the time constant of the system was able to be calculated from first principles modeling before the response curve was generated. In future problems, the time constant for the system will not be known beforehand, and so the 63.2% output value can be used to find what the time constant is from the graph of the response. There's an expanded quote by British statistician George Box. All models are wrong, but some are useful. It's important in control engineering that the engineer concedes that their model is just that, a model, not reality. But the engineer should also ask themselves whether the model they have created is useful. To answer this question, real-world data should be generated to confirm the validity, or rather the non-invalidity, of the model. If the model is found to be too sensitive or does not reflect reality, the effect of assumptions should be carefully considered, or a more sophisticated model should be employed. So let's recap. We wanted to know a particular feature of a system's response to a step input change, so we needed to make a model of the system. Because the system was relatively simple and its components easily understood and modeled, we chose to model it by first principles. After gathering the required information and making the appropriate assumptions, a differential equation was created by performing a mass balance about the control volume. The solution equation was then found by applying an integrating factor to make the differential equation separable and integrating both sides. The solution was then analyzed by testing limiting cases, and the requirements of the problem statement were addressed. Thank you for watching. I hope this video was helpful, and I'll see you guys in the next video. Bye.